as I mentioned, this is a technical webinar which is offered by the Benelux IEEE PES, IAS and PES joint chapter. It is given by our very, let's say, welcome Professor Xian Qin, one of our colleagues working in this area. He will give us today a seminar on power quality in electrical vehicle charging networks. And Professor Xian Qin is with the Delft University of Technology in the Netherlands. And actually, he received his bachelor degree from the Beihang University in Beijing in 2009, and his master's degree from the Beijing Institute of Technology, also in China. Later, he joined the Aalborg University for obtaining his PhD degree in 2015 in Denmark in electrical engineering, and in 2014, he was a visiting scientist in Aachen University of Technology in Germany. His research interests include power quality and stability of power thread-based grids and solid-state transformers, and he has published more than 100 journals and conference papers for book chapters to international patents, and also work in several European and Dutch national projects in these areas. He is a senior member, IEEE senior member, an editor of the Transaction on Industrial Electronics, and also a guest editor on other transactions as energy conversion and emerging and selected topics on powertrains. He is a distinguished reviewer for 2020. He has served as a technical product chair in different conferences, and actually he will be the technical product chair of the power electronics for distributed generation system that will be celebrated in Luxembourg in 2024 in June. Well, with this brief introduction, I would like just to give the word to our very good and welcome colleague Professor Xian Qin. And please, all the attendees, if you have questions, please put your questions on the chat, and we will address all these questions after his presentation. Okay, so Xian Qin, you have an audience waiting for you.
Okay, so I already admit that audience to join the webinar. So first of all, thank you, Pedro, for the introduction. And good afternoon, everybody. Welcome to this webinar. As Pedro has already mentioned, this afternoon, I mean, in the next half to 1 hour, I would like to have a discussion with you about the power quality in EV electric vehicle charging networks. So yes, the EV charging technology is developing very fast. You can see more and more EV chargers are installed in our grids, and the charging power is also growing very fast. Now we already have, let's see, electric vehicles which can handle around 300 kilowatt charging power. We also have chargers that can really supply even more than 300 kilowatt charging power. But the question is that because eventually all the power are going to be taken from the grid, so is our grid ready for this fast EV charging and massive fast EV charging? To figure out this question, we got some funding from European Horizon funding agency, and there our task is to focus on the power quality of EV charging station to see if in a few years we are going to have a massive installation of fast EV charging stations. Is there going to be a problem in our utility grid, and how can we solve that? There are, let's see, several different kinds of power quality issues. We did some investigation, and accordingly, we found that these listed here are those most relevant to EV charging. events. The first one is flicker. Flicker is kind of a low frequency fluctuation on the grid voltage. The frequency is very low, therefore it may trip the kind of flicker in neighbors lighting, so you can really see it. And the next is harmonics and interharmonics. They are located in the same range from around 0 to 2 kilohertz. The only difference is that the harmonics has an integer multiple of the fundamental frequency, while the interharmonics has those who has non-integer multiple of the fundamental frequencies are all called interharmonics. So if you do a measurement of the interharmonics, you will see something like this, which means on top of the fundamental, you will see something kind of unstable, right? It's resonating all the time. It's not because it is really something unstable. It's only because that item has a non-integer multiple of the fundamental frequency. So some people call it harmonic instability. Here I call it interharmonics. They are all the same thing. Well, regarding their effects to the grid, FC, first of all, they create loss in cables and transformers. As you know, harmonics, they do not transmit real power, right? So if you have harmonics, they only create loss. That's it. They also let's see, induce more operation or damage of devices in the grid. What does that mean? For instance, for this RCD device, residual current detection. I mean, as a common sense, you may know that it detects the leakage current, and as long as the leakage current is larger than 30 milliampere, the protection device is tripped. The switch is open, so the power is off. In this way, to protect human body or other equipments in the grid. However, this 30 milliampere is actually only at fundamental frequency. If in the leakage current there's a high frequency components, then according to some testing reports, higher the frequency, then higher the magnitude of current that can really get this RCD device to be tripped, which makes this safety level low, right? So I mean, people are already noticing this phenomenon, and they are looking into it and try to solve it. The last but not least is supraharmonics. It's kind of, I mean, in the past, people didn't pay attention to this, but recently, because of many power electronics are connected to the grid, and then people notice that there is also a component between 2 kilohertz and 150 kilohertz that are creating problems. And they give this a name as supraharmonics. So the harmonies it can do to the utility grid including the, again, more operation or damage of devices in the grid. As I mentioned, higher frequency of this item, then you need larger magnitude of current needs to trip the RCD device, and the same also for these supraharmonics. Besides it, because it's already in the frequency range of the power line communication, so it can also interfere with the power line communication. Okay, when we talk about power quality issues, some people may say, okay, we try to minimize the power harmonics or flickers, or we try to optimize the harmonics. However, what you really need to do is not to minimize or optimize them. What you need to do is you need to check the standard, and in the standard, there is certain limit stated there. You just need to make sure that the harmonics are not beyond that limit, and that's it. Usually you don't want to put more effort than that, because you get nothing, but you need to pay more because of the higher cost. So the only thing you need to do is you need to check the standard, make sure harmonics you injected into the grid is not beyond that limit. That's the thing you need to do. Because flickers, harmonics, and also interharmonics, they have been a problem for long. So standardization, according to them, are kind of mature. So there are already mature standards on those kind of power quality issues. I mean, not specific, not dedicated to EV charging, but I mean, EV charging, we can still refer to those standards. However, the standards regarding the supraharmonics is still ongoing. It's because supraharmonics is kind of relatively new phenomenon. Just recently started to get people's attention. So the standardization is still ongoing, and so far there is only compatibility level, but the emission level is not there yet. So therefore, according to there's not really regulation tell us what we need to follow regarding the supraharmonics, but the supraharmonics is are really creating problems, right? So as a researcher,
Sorry, Xian, you are muted. Okay.
Yeah, Professor, you are muted.
okay. So how about now?
Yeah, it works.
It's okay. It works.
Okay.
Yeah.
So I was just muted for this moment, right? Or I was muted till now?
Just for 1 minute, I think.
Oh, okay.
Yeah.
Okay, then it's fine. It's good. It's good. So yeah, okay. As a common sense, whenever talking about harmonics, you may say, okay, 5%, right? 5% THD. You have to, as long as you fulfill this, you know, the THD is lower than 5%, it's good. But if you open the standard, you look into it, you may see that standard states much more than this 5% THD. Actually, for each frequency range, you will see a certain limit of the harmonic current. And this limit is also related to the short circuit ratio. Why?
You are muted again, Professor.
Okay, I didn't do anything. I don't know if there's any attendee.
My fault, Xian.
Oh, okay.
It was my fault. Sorry.
Okay, no worries. Because what eventually matters is grid voltage distortion, right? And when you inject the harmonic current into the grid, and because the grid impedance is not zero, so due to Ohm's law, you will also indirectly induce a grid voltage distortion. But if the grid impedance is high, which means if you have a high short circuit ratio, you are allowed to inject more harmonic current. That's because even you inject more harmonic current due to this very low grid impedance, eventually the grid voltage distortion is still low. So eventually, what matters again? What matters is grid voltage distortion. So here I list a few measured results. They show that the power quality, different kind of power quality issues associated with each EV charging are already measured in the field. The first shows a flicker issue associated with 120 kilowatt charger at the bus station. the second one shows frequency beating due to two EV chargers with the same model, but due to they have a same model means they have the same switching frequency, but due to accuracy issue, their switching frequency can never be 100% the same. There's a very little difference, which is 2.5 hertz, and this 2.4 hertz difference in the switching frequency eventually induces frequency beating, which means the total current the two chargers drawn from the grid has a 2.4 hertz fluctuation, and eventually induce the voltage distortion at the same frequency. A third one is the supraharmonics measured at the grid side of the EV charger. And if you click into this link, you also see that the users, the Tesla users, also kind of claim that they had these flicker issues, or when they use Tesla charger to charge the motors. So it means the power quality issues associated with EV chargers are not something just a theory. It's already there in the field. So then the questions, we want to solve them, but first of all, we have to understand why there are these kind of power quality issues, right? For us as a researcher, we want to build up the mathematical model so that we can really find out the root cause, and as a next step, we can try to propose some mitigation measures. So we performed the measurement of EV charger, and we found that at the beginning of the charging procedure, there is a kind of a bump in the grid current. It's like a very high peak. It has a very short duration, but the peak is very high. And because of this surge current, there is a significant voltage drop induced in the grid voltage. Of course, this single event cannot really create flicker issues. By the way, flicker issues is also kind of a statistical indicator, right? But imagine that in reality, you may have several chargers in the same network, and so charging events are kind of started here and there. So eventually, a bunch of these kind of starting up of the EV charging will create flicker issues. So to model the flicker issues, what you need is a circuit like this. You can model the grid as a voltage source together with a grid impedance. So impedance is a word that I'm going to very often talk in this webinar. But every time I talk about the impedance, they are a bit different. For instance, for this, to model the flicker, you only need to know the grid impedance at fundamental frequency. That's it. Then on the charger side, you don't need to have to model the dynamics of the charger as an impedance. That is not necessary. What you need to have is a charging profile. You need to know the charging power as a function of time. That's it. With this, you can model the flicker issues. Then we ran some simulation, and we found that flicker issues are related to a few parameters, including the charging power. Of course, higher the steady state charging power, higher flicker issues you may have. It is also affected by the XR ratio of the cable. It shows that if the cable is more, let's see, resistive, then you have more chance yeah, you have more chance to have the flicker issues. It is also affected by the ramping up time of the charging. So if you want to reduce the flicker, then what you can do is to slow down a little bit the ramping up of the charging. It also shows that the short circuit ratio also affects the flicker, and of course, lower the short circuit ratio, then more significant the flicker issues can be. So then what would be the mitigation measures if you really have flicker issues there? Can you change the charging power? I mean, if the capacity of the grid allows you to go higher power, usually you go for that, right? You cannot, I mean, easily sacrifice this charging power because of the flicker issues. About this XR ratio, that is the characteristics of the keyboard. That is something you cannot easily change. Short circuit ratio, again, it's a parameter that you don't really have much freedom to change it. But what you can do is the ramping up time of the charging, right? Of the charging power. If there is really flicker issues, then the easiest way is to slow down the ramping up of the charging. The next is harmonics and interharmonics. For people who are working on harmonics, they should be familiar with this circuit model. So on one side, you have electric vehicles and EV charger. On the other side, you have the grid. The charger is usually modeled as a current source together with impedance in parallel. Then the grid side is again modeled as a voltage source with a grid impedance. But you need to pay attention that here the impedance is not a single value at the fundamental frequency. It's a broadband impedance. And usually you need this impedance value from 0 to up to kilohertz to study the harmonic and interharmonic issues. So if you have a circuit model like this, and you can calculate the voltage or current at PCD point. Here I just show an example. How is the voltage at PCD point? Sorry, the current at PCD point calculated. It is a function of 4 parameters, right? It will be affected by this voltage source, which is the background noise of the grid impedance, the charger impedance, and also the harmonic emission of the charger. So it's a total effect of all these 4 parameters. However, if you think about it, the harmonic emission of the charger shouldn't be a problem, right? Because if the charger is allowed to be connected to the grid, I mean, before that, it has to pass through some certification. And in those certification, the charger will be tested and the harmonic emission will be tested. And it has to follow some, let's see, to make sure the harmonic emission is below some limit stated in the standard. So if there is a problem at the harmonic or interharmonic problem at the PCD point, it shouldn't be the reason of this harmonic emission. Then the background noise. I mean, the grid operator will make sure the background noise is in a, let's say, acceptable range, right? So it might be high, but still be in a acceptable range, I would say. But eventually, you may still have the problem. Then I would say it's mainly because of the mismatch in between these 2 impedances. Which means if you look at this equation, the harmonic current, here I show the harmonic current at the PCD point. If you calculate the harmonic voltage at the PCD point, you will get a similar equation. which means the denominator will be the same. So if the denominator has a let's see, eigenvalue with a positive real part, then this grid connection will become unstable. Even if that's not the situation, let's see, the denominator may have a value which is close to 0, right, at a certain frequency. In that situation, even the grid connection is stable, but due to this very low value of the denominator, the harmonic emission, the background noise, can be very much amplified at the PCC point, and eventually you will see harmonic issues that is beyond the limit. So to briefly summarize, if there is harmonic or interharmonics issue, very likely it's because of the mismatching between the two impedances. Then how can we, if there is such a problem, how can we solve the problem? Or when we design the EV charger, how can we beforehand to evaluate there is going to be this problem or not? So we need to model the impedance, right? Apparently, the way to model the impedance of the charger has you basically you have a few options. The very widely used is so-called black box measurement. What you do is you connect the charger to a grid emulator and use the grid emulator to inject voltage perturbation to the charger. Then as a response, the charger will also give you a current perturbation, and the ratio between the voltage and current perturbation is going to be the impedance. Then you do a frequency sweep, you get a broadband impedance of the charger. The approach is widely used, but if you look at the quality of the approach, see you may get a large error if the current perturbation is very small, right? You inject a voltage perturbation, you cannot make it large because this is, let's say, a small signal approach. But the impedance at that frequency could be high, so which means the current perturbation will be very small. And you have a resolution of your measurement, right? In that case, there will be the measurement can give you very large error. You may also get a large error in the phase measurement at high frequency. Let's see, if the frequency is close to kilohertz, you want to measure the phase of the current perturbation. It can also gives you a large error. So then another approach to avoid these errors in measurement could be this analytical impedance model. So here you want to model the input impedance of the EV charger. Then what matters actually includes the power filter of the front-end converter, and also the control of the front-end converter, right? And if you let's see, open the charger, look into the control structure of the front-end converter, you will see that it is composed of several different controllers, including the DC side voltage control, the PLL, the current control, and also modulation. The next thing is you build up an analytical model based on this control and also power filter. Each part will have an influence on the impedance, of course, but at a different frequency range. So in the end, if you notice harmonic issues, then according to the frequency of that harmonic issues, you can easily trace back which part of the control creates that problem, right? Then you can accurately fine-tune that controller to solve the problem. So that's advantage of this analytical impedance modeling. However, in this project, what we eventually encountered is that in order to build up the analytical impedance model, you need to know the control structure of the charger. You also need to know the control parameter values of the charger. The things, I mean, these kind of details only the charger manufacturers have, right? And you cannot, we as researcher, or let's say if a grid operator or charging point operator wants to perform such a study, they cannot easily get these parameters, parameter values, or the control details. Or even if you let's say collaborate with charger manufacturers, try to find out these control details to build up the analytical model, and usually you will see even them cannot easily give you an answer like, you know, the control structure is like this, the control parameter values are like that. So in the end, you need to find out these parameters yourself, or it becomes a half black box, half open box issue, and we call it a gray box modeling. What does that mean? I believe if you are working with power electronics, I believe you may have experience with impedance analyzer. For instance, if you want to design an inductor or transformer, if you care about the parasitics, then you use an impedance analyzer to measure it, right? Then it can really tells you what parasitic capacitance the inductor may have. But sometimes you may make something more complicated. You may have let's say a passive network which is composed of several inductors and several capacitors, and you want to use the impedance analyzer to measure the impedance. In that case, when you after the connection between the component and the impedance analyzer, the next step should be you have to tell the impedance analyzer what kind of a model you want to measure, right? Is it a kind of series connection between inductor and the capacitor, or is that a parallel connection between inductor and capacitor? You need to first tell the impedance analyzer that, and that's the only knowledge you need to tell the impedance analyzer. Then it can really, by curve fitting, model your passive network very well. The same idea is also used here. Okay, we don't know what kind of control structure is used in the front end AC/DC converter, but how many options can be there? Not many, right? With I mean, for instance, for myself, with many experience in power electronics, I know there are a few options existing there. So you can actually, what you can do is to build up a library to cover all these different options, right? And you can try each of them. Let's see, first, maybe in the first step, you assume such a control structure is used in that converter. Of course, you want to have some a measurement, but you don't need the measurement with very accuracy. You need some basic measurements as an input to the this modeling approach. Then you make a guess. You assume a certain control structure is used in that EV charger. Based on this, you can try to by using some optimization algorithm, you can try to extract the control parameters, right? Maybe eventually you failed because you made a bad guess. You didn't I mean, the control structure that is really used in the converter is not the one that you assumed. Then you can change it, right? You go to the next one in your library because there's only a few options in your library. So eventually you will, you may choose the correct one and make a good extraction of the parameters. So we tried this approach, and then we figured that there are the problem is more complicated than what we thought. The thing is, there's not only one. There is not only one parameter that needs to be extracted. There are several, and they are coupled together. Then it becomes a non-convex optimization problem, right? If there's only one parameter, it's a convex optimization problem. It's easy to solve, but there are many parameters coupled together. It becomes complicated, and eventually the optimization may even diverge instead of converge. But then we found that the control parameters, they actually have influence at different frequency ranges. And our idea is that can we find a frequency range that only one parameter is really influential. And then from there, we can at least extract the first parameter and gradually, follow this idea to extract other parameter values. Then we tried this, it worked. I have to say it's not 100%, it's not perfect. For some parameters, they are still kind of coupled with another parameter, and you can hardly really decouple them between them. But it works to some extent. And based on this approach, we build up this grid box impedance modeling, and it is published in the power electronics transaction in this year. This in this slide shows test facilities in our lab that we use to do the measurement, to measure the impedance, to verify our impedance modeling approach. Okay, that is still about modeling. So with the modeling, you may evaluate the harmonic issues. It might be that there will be harmonic issues. Then what will be the next step? You want to solve it, right? As I mentioned, if there's harmonic or interharmonic issues, then it's because of the mismatching between the two impedance, the charger impedance and the grid impedance. Again, grid impedance is not something you can easily change, right? I mean, it's time variant, but that is what it is. You cannot really change the grid impedance easily. But what you can do is to change the charger impedance. So what we did is we tried to reshape the charger impedance and making the mismatch become match. Then, okay, from this figure, by the way, this blue and red, they are the grid current. You can see that once the impedance shaping functionality is enabled, the harmonics in the current becomes much smaller. So what is impedance shaping? As I mentioned, the impedance of the charger is affected by the power filter, but it's also affected by the control. You do not often or easily change the power filter of your charger, right? But you can easily change the control. So impedance shaping is actually kind of a control tuning, but it's you look at this from the impedance perspective, so that you can do the fine tuning easier. That's the idea. The third one is the supraharmonics. Again, to study the supraharmonics, you can use a similar circuit model. But the difference is that the impedance will again be a broad band impedance, however, at a higher frequency range, right? So it is in such a frequency range, which is, by the way, larger, higher than 2 kilohertz, that the impedance becomes quite resistive. Therefore, this impedance network will very likely be over damped, which means if you still see a let's say supraharmonic issue at this TCC point, it is not because of the harmonic emission is amplified or the background noise is amplified here, right? Because it is a very over-damped impedance network. So I would say the harmonic at the TCC point can only be lower than the harmonic emission from the charger or the background noise. So if you still see the problem, then you should try to look into this one and that one, and try to reduce them. And that is the way to go. Again, you cannot easily change the background noise of the grid, but you can look into the harmonic emission of the EV charger and try to do something there. So in another European project, our role is to design the power modules for fast EV chargers, including the front-end AC/DC converter and the back-end DC/DC. So when we study this front-end AC/DC converter, we pay extra attention on these supraharmonics, and we proposed something. First of all, we found that usually the converter uses fixed switching frequency, right? But with fixed switching frequency, you will have the switching frequency noise very concentrated. So then what we tried is to use a variable switching frequency. You can vary the switching frequency in different profiles, right? It could be a sinusoidal profile or triangle profile. But by doing this, what you achieve, we will achieve is first of all, still the same THD. That is not going to change, but switching frequency noise is going to be more evenly distributed. Well, we don't have a emission level for the supraharmonics yet, right? Standardization is ongoing. But assume we will have, then it's going to be similar with low frequency emission level, right? What they do is they draw a line, horizontal line for a certain frequency range, and in this range, all the harmonics should be lower than this line. That's what they usually do. Therefore, with this variable switching frequency, because it's more evenly distributed switching frequency noise, then it's easier to fulfill the limit, right? If there is going to be a limit, and I believe there will be in the near future. So we also build up a prototype and implement this variable switching frequency, and this is our test results. So here we have a fixed switching frequency. You can see the peak of the switching frequency noise is around, yeah, it's larger than 1%. But by using variable switching frequency, you will see that it becomes much lower. We also tried different profiles. This is an sinusoidal profile, this triangle profile. Then we also tried different reference shape, right? The reference, the basic one is a sinusoidal, but we can also have this SV, right? With a third harmonics injection and some other reference shapes. Another thing is, okay, what you can do is you can, by the way, we have to go back to this slide. You vary the switching frequency, and then you give a band, right? You give a band of this variation. If you want this switching frequency noise to be more evenly distributed, then you should increase the band. The band should be larger. But then you will have a risk that they are so, let's see, widely distributed, and in the end, they may have an overlap with another order of harmonics. Well, if you have a high switching frequency, here we have the switching frequency around 24 kilohertz, so it is not really a problem. But in some other applications, you may have low switching frequency, then you may have a high chance to encounter this overlapping, then create another problem. To solve that, we propose to have an interleaved converter with variable switching frequency. With the interleaving, what you will achieve is the cancellation of the odd order switching frequency noise, right? Therefore, the how do you call it? The neighbor switching frequency noise will have a long distance between each other, and you will have less chance to eventually encounter this overlapping. Well, this work is still under review, so I cannot share more details. But hopefully it will be accepted. So next time in my talk, I can tell you a bit more. So then the summary for flicker, I would say the reason is mainly because of the starting of the EV charging and of frequency bit between two chargers. In order to study it, to model it, you need a grid impedance model at fundamental frequency. You also need to know the charging power profile, especially during starting up and shutting down. For mitigation measures, I would say if you have the problem, you may want to limit the charging power ramping rate. For frequency bit, I would say try this variable switching frequency. Well, we haven't got the results yet, so this I put a question mark here. For harmonics and interharmonics, if you have such a problem, I would say it's because of the underdamped impedance network. And to model it, you need to have this broadband grid impedance and also the charger impedance. To solve it, you have to make the mismatching becoming matching, right? So we tried to use impedance shaping approach to do it. It's actually a controller tuning approach. For supraharmonics, if there is such a problem, or if it's creating problem, then I would say it's mainly because of the modulation and also sometimes the commutation between switches. Because the frequency is high, so I wouldn't try to model the impedance network accurately, and it's difficult, right? You have a skin effect. Some other parasitics also playing a very important role at the high frequency range. I wouldn't do that. I will try to focus on the switching frequency induced noise, and I try to reduce that. We tried with this variable switching frequency, and it works. Perhaps there are also some other advanced modulation schemes. So here, if you are interested, there are a few more publications for further reading. And also, before I finish, I want to acknowledge my PhD students, Lu Wang and Yang Wu. They have helped a lot in this study. That's all about my presentation. Thank you.
Thank you very much, Jan, for this very nice, really presentation and this very nice webinar. Actually, it was very interesting to me. Yes, now I am wondering, maybe I will just during this time to share the screen with the, or maybe you can share the screen with the, yes, with the banner of your, or maybe some slides will be required to be shared for answering the questions. Well, now, so first of all, really, thank you very much. Very interesting. I will, well, if anyone from the audience have any question for Professor Xian Qin, is this time for set then on the chat, okay, or in the chat. In the meanwhile, maybe I have some question to you, and let's see, in such a case, please. Maybe we can animate a little bit the audience to put some question to you.
Yeah.
Well, my first point is regarding all these power quality issues that you have been mentioning, I guess could be affecting to the distribution level, low voltage level with higher impedance, so you are considering also these effects could give rise to impact at higher levels, not only distribution, but also considering future large electrical vehicle charging infrastructure could be also affecting to, for example, modes, new modes, or new low frequency oscillations in transmission system level.
Yeah, So actually, I was in a webinar given by a DSO. We have done some survey, and according to the survey, they see less emission level or less harmonics in the transmission grid, but more harmonics in low and medium voltage grid. So this is a trend they see. And actually, our work so far, we mostly focus on the power electronics. Okay, you see that in our model, we have to also consider the grid impedance. So then we get the grid impedance as what it is. We cannot really do much about it. And we focus on power electronics, because for power electronics, we can really do something. If there's a problem, we will say, okay, how can we change the design of the power electronics to solve it?
Okay.
Yeah, so I would say that maybe in the future we should pay more attention to the medium voltage grid, because now people are talking about very high power EV charger or even charging infrastructure for heavy duty trucks. There it will be a megawatt, tens megawatt, very high power. So you have to take the power directly from the medium voltage grid, because low voltage grid cannot handle that power. Then what will be the influence there? I think in the future we will also pay attention, put some effort on that aspect. Transmission grid, charging, I don't know. I'm not sure.
Okay. So thank you. Well, here we have a question. Thank you. I mean, is the impedance matching possible to do in real time dynamically? What is this approach?
We haven't tried to do it in real time. So what we did is we build up the model, we perform an evaluation and see if there is a problem. And we saw the problem, then we fine tune the control, right? Impedance shaping is actually a tuning of the control, as I already mentioned. And then we check it again, see if it's the problem is still there or if the problem is solved. So we do it kind of with offline approach. I would say that, okay, in reality, the impedance of the charger can change. It changes according to the different operating points. The grid impedance also changes, right? I saw some measurement about grid impedance. It's not a steady one impedance curve. It's so eventually the measurement results is a root log high. It's a time variant impedance and it changes all the time, but you can use this kind of envelope to cover all of them. So what you need to do is when you design the charger, you have to make sure the impedance will match even in the worst case. If you make sure that is going to be the case, then you can even you do it on offline, but you can still solve the problem. That's my understanding. Yeah.
Okay, and we have another question here regarding supraharmonics, which are reported in fast charging sessions. And there are two questions in this regard. Okay, and this is from which kilowatt level this phenomena is seems more relevant or more seen. Okay, what is the relevance from what power level, and what is the risk disadvantage of variable switching frequency as a mitigation strategy?
Okay, regarding this power level of the supraharmonics, so the real measurement in the field we got is I believe that's about okay, let me quickly go back to that slide. I believe it's more low power charger, but the thing is that for high power charger, they usually go with a modular design, and the power module usually has let's say 30 kilowatt, which means if you need a 90 kilowatt charging power, you put 3 there. If you need 150 kilowatt charging power, you put 5 there. So as I mentioned, it's more about the switching frequency. So in the end, the switching frequency will not change because of the total charging power. Therefore, I don't think the power really matters a lot unless you change the way of the charger designing. Otherwise, I wouldn't see the power will be very relevant to the supraharmonics. Then the next is the risk and the disadvantages of variable switching frequency as a mitigation strategy.
Hi, Zian.
Yes.
Can I have an add-on to the question?
Sure. Go ahead.
So, Mohammed, regarding your first question about the supraharmonics, because I'm young, I'm doing the supraharmonics with a periodical variable switching frequency. So usually, from my point of view, this switching harmonics in the supraharmonics range is generated by the modulation, and the modulation harmonics is directly related to the voltage. So if your operation power is proportional to the voltage level, for example, in the medium voltage level with high power, then this relation remains because your generated voltage harmonic is directly related to the voltage. So the conclusion or the insights are basically the same in the low voltage distribution grid application and also the medium voltage application. But in case in the high power but with lower voltage, that I don't see it often, but in this case, the direction might be overtuned because this needs a more detailed check. Because in our case, usually we think in the medium power, usually you use this modular design or either use the medium voltage transformer. Then yeah, the subharmonics is still following the same and this spread harmonic with periodical variable switching frequency. So I think so. In short, you can regard in the medium voltage level and low voltage level, the conclusion are the same. Yeah, and also for the risks, that is kind of direct because I said the THD is remain the same after this variable switching frequency, but this is specific to the voltage. After filtering with the L filter or LCL filter, this variable switching frequency will induce a bit larger THD. That is a drawback. Yeah.
Yeah, but for example, Siam, what about the filter design? Because now your bandwidth at the LCL filter should be wider, no? And what is it? I understand it will have a given economic impact and even regarding efficiency, doesn't it?
Actually, unless you make you have a variable switching frequency and you have a band, right? You shouldn't. Yes, first of all, you shouldn't make the band let's say too big. There's a ratio between this band and the main switching frequency. You should make this ratio large. So as long as you keep it small, then there is no big difference in terms of the loss, the switching loss. We tested and that is verified. But the thing is, okay, you want to get this switching frequency noise more evenly distributed. In that way, you want to make this band not too narrow, right? If it's too narrow, it not really effective. So what will happen, right, is that the switching frequency noise will kind of extend on both ways, to higher frequency and also to lower frequency. To higher frequency, you don't care because there the filter will give a higher attenuation. Noise will be even lower, but it also extends to the low frequency. There you have a low attenuation of the filter. So there is a trade-off. There's a trade-off. Yeah, and you have to take that into consideration.
Okay. In the meanwhile, we have any other question. Once I know, Sian Kin, you are making today an effort because you had some problem with your voice. Therefore, I would not like to stress you too much. So really, we appreciate a lot your speech. But
Thank you.
maybe let me put you a last question, at least from my side. What is regarding this impedance detection from the power converter, because at the end of the day, this is a topic that has been explored for many years from many different applications. And the problem, at least from my perspective, is the impedance estimation is a cause-effect relationship. Okay, you generate a perturbation and you see what is the variation in current or voltage.
Yeah.
But what about when you have several converters working in parallel trying to do the same? How could they manage to know what they see is because of their perturbation, what they see at the point of connection is because of their perturbation, or is because the other were perturbing the grid, and eventually maybe you are detecting something which is nothing to do with the impedance actually of the grid, because the other ones are also generating a variation in such a voltage relationship, no? Voltage current relationship, that's it.
So yes, I would say that if you have several converters connected in the same network, each converter needs an impedance. And then what you can do is you can build up this network model with based on those impedance model, and you can still check if there is going to be a resonant point or not. But in general, why nowadays the problem becomes becoming more significant is because more power converters that you connect to the grid. I would see that. It's like that the short circuit ratio is or equivalent short circuit ratio is becoming less, right? The grid is not changing, but you are connecting more and more. And okay, because the conventional control that we use for those converters, and it becomes more problematic when the SCR short circuit ratio becomes low. You will see more resonance, and even you see less stability. That's a major reason. But there can be different converters. They can have different impedance. Then the combination between them can be complicated. That I agree. That's why there we need this let's say simulation softwares, right? Which can do system level simulation to check.
But my question was, I mean, of course, when you analyze everything offline, you can estimate what is the impedance or what is the contribution of each. But I was thinking, when you are trying to implement, as one of our colleagues mentioned at some point, if you try to estimate this impedance online in real time, you never will know if the perturbation you are measuring is because of your excitation or because other is the one generating that. If that's the case, I understand we need to have some kind of synchronization between different converters or any kind of rule, no? At that level, no?
Yeah, that's a good question. We didn't really consider about this with what we did. We did the measurement offline. So it's going to be the one charger, one grid emulator. But I also saw people kind of doing this online impedance measurement. There will be a chance that many chargers are operating simultaneously. How much that will affect this impedance measurement, I do not have a clue yet. But that is definitely an interesting topic to look into it. Yeah,
I agree. So I don't know if we have any other question from our audience. Well, if done so, maybe it would be great if we could activate our camera and we have a common picture of all of us here today in the session, or at least for eventually reporting. I don't know if you would be able, Sian, eventually to take a picture of all of us, okay, a capture of the screen.
Yeah, I can try. Let me try.
And in such a case, later we will share it all together. And thanks all for meeting here. I hope you enjoyed the meeting, the webinar. Actually, it was a very nice topic and well, the impact of electrical vehicles will have different facets in our current grids, as expecting this electrical vehicle penetration in the future, in the very near future, will be something the grid will not be able to withstand. I mean, we are talking, or we are most of us paying attention to the security of the grid, from the security of energy or power supply, but these problems that Professor Xian Qin today is talking about, the power quality will be more and more relevant as well, okay, and will give rise to very new or very relevant issues. So I consider this really the presentation and lecture was really welcome, or very timely and relevant. And really, thank you very much, Xian, for this lecture.
Thank you.
I don't know. Did you take a picture, Xian?
Yes, already done. It's done. Yes,
Okay,
I will send it to you.
Thank you. So we will do something. I mean, I will send you, I think I will send an email to all the ones registered in the seminar, even the one didn't attend it, and we will share a link to the record of the session and also to the slides that we shared today in this session, okay?
Yeah.
And I hope to see you in future sessions. That I mean, my intention is to promote more of this, and actually I encourage you and I invite you, if you have interest in sharing your research topic and you want to give a webinar, you are all more than welcome to have this discussion for a while and to be able to know each other through this Benelux chapter on the PERS, IAS, and PES joint societies, let's say. So really, thank you very much all for attending. Thank you very much for this very nice presentation. And well, I hope you enjoy, and I hope we all will meet in future events. Okay?
Okay. Thank you, Pedro. Thank you, everyone.